precursors for this chemistry as well. And in the case of terrestrial biochemistry, these sort of basis set of organic life consists of the elements carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So what we would love to know is, in addition to being rocky and having surface liquid water, do these habitable planet candidates also contain these 6 biogenic elements in the right proportions for life to emerge? But unfortunately, characterizing the volatile inventories of rocky exoplanets is going to be extremely challenging until at least 2040, when we may have sort of next generation NASA flagship missions. So instead, we can characterize the chemical environments that planets are forming in to give us a really unique way of understanding how planets are seeded with these biocritical elements, studying the process of planet formation itself. So when I talk about sort of the delivery of prebiotic building blocks, there's 2 angles that we can take in thinking about this. The first is to try to understand the total inventory of biogenic elements in planet-forming gas and solids. So just what is the sort of total reservoir of these different elements that's available? The second approach that we can take is to try to understand the form that these elements are delivered in. So what is the degree of chemical complexity that's being delivered to kind of planet-forming material? And are any prebiotically useful molecules actually delivered already kind of prior to the planet formation stage? So we don't yet know how exactly life originated here on Earth. And so both of these angles, I think, are still valid and important, and you'll see kind of both perspectives throughout this talk. So how do we probe this very challenging question of what is the chemistry of planet formation? So we have many different tools at our disposal to address this question. And I'm going to walk through this schematic now to show how we can use all these different pieces to assemble a complete picture. So the first thing that we need to consider is that the volatile elements that we're interested in can either occur in the gas or the ice phase in these star and planet forming regions. This is important because the gas and ice phase actually have very different behaviors that lead to very different kind of chemical outcomes. So when you think about the very low temperatures and low densities of interstellar space, it places some constraints on the types of chemistry that's able to proceed, meaning that when reactions are happening in the gas phase, they only are really efficiently proceeding through reactions between ions and neutral molecules. And this leads you to build up some really kind of exotic and interesting molecules like these long unsaturated carbon chains, which are fun and interesting, but not necessarily directly relevant for origins of life chemistry. If you want to form the organic molecules, we think that this instead happens on the surfaces of dust grains. So interstellar dust is a kind of ubiquitous component of the interstellar medium. And in cold, dense regions, volatile molecules condense out onto the surfaces of these dust grains. And this basically allows you to get around some of these constraints on the chemistry that are imposed. So the result is that when chemistry is happening on ice surfaces, you're actually able to produce organic molecules. And as a note of terminology, astrochemists call any molecule that's 6 atoms or bigger a complex organic molecule. We should know that these are not complex by any terrestrial standards, but it is sort of at the limit of chemical complexity that we can detect in through astronomical methods. So the next thing that we care about is studying the chemistry along all stages of the star formation sequence. We know that planet formation is actually just kind of a byproduct of the formation of a low mass star like our sun. This process begins in the molecular cloud where you have kind of dense gas, and at some point a region of the cloud will begin to collapse in on itself, forming a protostar. And the protostar may form sort of a protostellar disk, and the whole system is still in this stage embedded in its parent envelope. At some point, the envelope is dispersed and you're left with just this protoplanetary disk, this flattened structure in orbit around the star. And it's in the disk stage that historically the planet formation process was thought to take place. So you have these high densities in the disk midplane that's really facilitating the production of larger bodies like planetesimals. And then lastly, anything that is not incorporated into planetesimals is swept out of the system and you're just left with your isolated planetary system. So we really need to study the chemistry at all of these stages leading up to planet formation, because as we'll see later, there is some continuity of the chemistry here. And so we gain really valuable insight by following this entire kind of thread of star and planet formation. So the last thing that I'll talk about here is that we have three main tools in our astrochemical toolkit that we can use to approach this problem of planet formation chemistry. So these tools consist of lab experiments, models, and observations. And observations are really valuable because they give us constraints on the abundances and distributions of molecules that we can observe. And they also allow us to probe the physical environments that this planet formation physics and chemistry is happening in. Lab experiments allow us to make really robust measurements of the microphysics and chemistry at play in a very controlled setting. And then we can use astrochemistry models to sort of put these pieces together and make predictions for how the chemistry plays out in much more complex environments, which is especially important for predicting the compositions of the abundances of molecules that we can't directly observe. So all of these pieces now we can kind of combine to assemble a more complete picture. And I'm going to be using this schematic as a guide during the talk, where you can basically take one segment from each layer, depending on what question we're trying to address. So as a roadmap for where we're going to go with the science part of this talk, we'll start by thinking about how chemical complexity is built up in the early stages of star formation. We'll then consider what of this early complexity actually survives the processes of disk formation and evolution. And then lastly, we'll think about what the role of reprocessing in the disk plays in terms of setting kind of the ultimate available volatiles in planet forming regions. Okay, so let's start with this first question. Now, a kind of surprising development in recent years is that complex molecules are actually being routinely detected in the earliest stages of star formation. And it's not actually obvious how you can build up chemical complexity in the very cold and sort of energy poor environments like molecular clouds and protostellar envelopes. So I've been really interested in understanding or addressing this question: how can we explain the production of chemical complexity in cold interstellar regions? So like I said earlier, we think that the chemistry leading to the production of organic molecules is happening in the ice phase. And there's different microphysical processes in the ice that are regulating the production of organics. So the processes like accretion and desorption set the composition of your ice. Within the ice, you can have processes like diffusion and reaction that lead to the production of new molecules. And then there are also photo processes like dissociation and desorption that can be induced by the absorption of a photon. So we really need to understand how all of these microphysical processes work in detail in order to explain how organics are forming in different interstellar environments. So luckily, we have lab experiments that allow us to test just this. So we're going to be thinking now about ice experiments in the lab. So I'm showing here the ultra high vacuum setup that I worked on during my PhD. This chamber allows us to achieve pressures that are about 13 orders of magnitude below atmospheric pressures and temperatures as low as about 10 Kelvin. So we're really kind of mimicking interstellar space-like conditions. This is just a schematic of the different instruments that we have at our disposal in the chamber. So we will deposit volatile molecules that we're interested in studying through this gas inlet. The cesium iodide window is cooled down to about 10 Kelvin by the helium cryostat. And so the volatiles that we release into the chamber condense on the cesium iodide window, forming our ice sample. And then we can use infrared spectroscopy to study the composition of the ice throughout the course of an experiment. And we can also use energy sources like a UV lamp to sort of stimulate the chemistry. So again, the sort of driving question here is to try to understand what ice phase pathways can actually lead to the production of organic complexity in very cold interstellar conditions. So I'm going to talk about one example of this type of chemistry that we think is especially promising, and this is chemistry involving excited state oxygen atoms. So it turns out that when you energetically process common oxygen-bearing ice molecules like CO2 or water, you produce an electronically excited oxygen atom or an O singlet D atom. So in the case that you irradiate CO2 molecules at Lyman alpha wavelengths, your products are CO and then one of these excited oxygen atoms. So in the gas phase, we know that these oxygen atoms have a very special property where they can insert directly into the carbon-hydrogen bond of hydrocarbons to form an organic. So here's an example showing methane reacting with oxygen to form methanol directly. And in the gas phase, we know that this chemistry proceeds with no energy barrier and has a very favorable formation of your organic product. But in the gas phase, you can't actually stabilize this product molecule, and it actually tends to fragment into sort of smaller pieces, meaning that this oxygen insertion chemistry is not allowing you to build up more chemical complexity in the gas. So we were very interested in testing what the energetics and products of this type of chemistry look like in the solid state. So we designed an experiment that would allow us to isolate the chemistry of these excited oxygen atoms. So what we do is we deposit a mixture of methane and O2, and then we irradiate this ice with wavelengths of light that can only dissociate O2. So we're really kind of selectively following the chemistry that's leading from these oxygen atoms as they are formed and then insert into methane to form methanol. So we want to understand what the energetics of this process are, and to do so, we need to model the kinetics. So here I'm showing an example of a infrared spectrum over the course of the experiment, and you can see that we are indeed producing methanol quite efficiently. And on the bottom, you see the growth curve that just describes the production of the molecule over the course of the experiment. And so we can fit this growth curve with a kinetic model describing the rate of the methanol production. And then we put it on this type of plot where we look at the rate constant as a function of temperature. So the key here is that if there's an energy barrier to this reaction, the slope of this plot will be proportional to the energy barrier. But when we run these experiments at multiple temperatures, we see a flat slope. So what this means is that these oxygen insertion reactions are proceeding with no activation barrier, which is great news if you want to form organics in very cold environments, because this type of chemistry will still be active. So we can do more than just understand the energetics. We can also sort of mechanistically understand how all of the different molecules within the ice that we're forming and destroying are connected to one another with this type of mechanism diagram. And we can also constrain the branching ratios for how different molecules are formed throughout the experiment. All right, and we obviously want to know if we can make organics beyond just methanol. So the next step was to see whether this type of chemistry can actually proceed in larger hydrocarbons. So we tested oxygen atom reactions with the C2 hydrocarbon series. And indeed, we find that a whole suite of different oxygen-bearing organics that are fairly large and complex can be produced by this type of chemistry. So what's exciting is that we can look at interstellar ices along protostar lines of sight, and we see that many of the features correspond to these large oxygen-bearing organics that we can produce through this type of ice chemistry. So it's exciting to think that this oxygen atom chemistry can be contributing to the production of complex ices that we see in real interstellar lines of sight. So I've shown how we can use this type of ice chemistry experiment to help us understand the origin of organic molecules in the early stages of the star formation sequence. And I want to emphasize that this is actually quite important because we think the chemistry in these early stages is actually inherited through to the planet formation epoch. So this is just one example of many, many lines of evidence suggesting that this inheritance is present within our own solar system. So you can see the organic composition of low mass protostars compared to comets here. And we notice that they're actually quite similar to one another. We also have lines of evidence like isotope fractionation levels and so forth that really point to chemical inheritance from the earliest stages of star formation, shaping to some extent the compositions of icy bodies within our own solar system. So this brings us to the second question of this chemical complexity that is built up in the early stages. What actually survives disk formation and evolution? So first, let's just think about whether inheritance is actually plausible. So we know that disks, the regions where planetesimals and planets are forming, have very steep temperature gradients in the vertical direction that's resulting from the kind of irradiation of the disk surface by the star. So in the upper layers, it's very hot and very heavily irradiated. And then as you go deeper into the disk, it becomes colder and more shielded from this destructive radiation. So in principle, ices that are incorporated into the midplane of the disk should be well protected from reprocessing and should be available for incorporation into icy bodies. On the other hand, we know that disks are dynamic objects. So we have processes like vertical mixing and settling, as well as radial drift that is redistributing material throughout the different radial and vertical zones of the disk. So given this dynamical context for disks, we're interested in understanding whether it's actually plausible that interstellar ices can survive their journey through the disk. And so for this, we're going to shift to thinking about models of ice chemistry in disks. So we developed a simulation framework to allow us to explore this question. The physical model of the disk is a particle tracking model that follows individual dust particles as they're subject to processes like turbulent mixing, vertical settling, and radial drift. So here you can see an example micron-sized particle initialized in the disk midplane, and over the course of 1 million years, it's wandering through many different environments within the disk. We couple this physical model with a chemical model that's based on a protostellar ice structure and composition. So this has a water-rich core with other molecules that are normally associated with the water-rich layer, and then is capped by a thinner CO-rich layer. So we then subject this ice to destructive processes like thermal desorption, photodesorption, and photodissociation to see how the ice is basically altered as the particle is journeying through the disk. So I want to give you some examples of how this plays out in some sample trajectories. So here we're looking at a 1 micron size grain initialized at 20 AU, and you can see that the particle is sort of moving initially just within the midplane and then eventually wanders into the more UV exposed layers of the disk. So what we're seeing in the right panels here is the UV flux. And then in the far right panels, we're looking at the thickness of water and CO ice at a given time. So the pink is the sort of parent molecule and the orange is its dissociation product, which we track separately. So in the inner disk, we see these really sharp pulses of destruction corresponding to the kind of intense bursts of UV that these particles are exposed to. By contrast, here is a micron-sized grain initialized at 50 AU, and we can see again the particle starts wandering in the midplane of the disk, and it wanders a little bit further away from the midplane, but because the UV field is less intense in the outer disk, we actually have a more kind of gradual exposure to UV, and you can see that the ice processing is correspondingly a little bit kind of more gradual throughout the particle's trajectory. So the takeaway here is that when we couple physics and chemistry in this way, we see very different ice loss outcomes for different grains. And this is controlled largely by the efficiency with which a particle is transported into the UV exposed layers of the disk. So here I'm showing a sort of synthesis of thousands of these particle trajectories where the radius is increasing from left to right, the initial radius that the particle is placed in the midplane at, and the grain size is increasing from top to bottom. So the sort of important trends to note are that as you move from the inner disk to the outer disk, the particle is more efficiently lofted away from the midplane. But like I said before, the UV gradients are shallower in the outer disk, and so these particles will be exposed to more kind of gradual, gentler ice processing compared to the inner disk. In terms of grain size, as the particles grow in size, they experience less lofting away from the midplane, but they also become more subject to radial drift. And so by the time you reach about 1 millimeter in size, the particle is going to spiral pretty efficiently inwards towards the star. So you can see how with thousands of these trajectories, we can now start to assemble some statistics for how ice loss is going to proceed in a dynamical disk. So here now we have a summary plot showing how the fraction of the original ice mantle that's left intact after 100,000 years for particles initialized at different radii in the disk, and the different colors are showing the 4 different grain sizes that we tested. So for small grains less than about 1 micron in size, we see that they're actually really efficiently losing their ice mantles at the comet forming radii in the disk, which is between about 5 and 30 AU in our solar system. On the other hand, larger grains, 100 micron to millimeter size, are experiencing virtually no ice loss anywhere in the disk on these timescales. So the interesting take home here is that it's actually difficult to explain inheritance in comets if they're forming through the hierarchical assembly of local material. So you can't start with small dust grains and grow them to larger sizes at the comet forming regions of the disk while still preserving the ices intact. Instead, we think a more plausible pathway to inheritance is to grow to pebble sizes at larger radii and then drift this material inwards to the comet forming zone. So even the small particles in the outer disk are losing only about 10 or 20% of their original ice mantle. So if you start with these small particles, grow them to larger sizes, they will have most of their ice mantle still preserved, and then you can drift this material inwards, feeding it onto forming planetesimals. So this pebble drift and pebble accretion framework is actually gaining steam as a way to explain planet formation physics in our solar system and others. And I think it's really exciting that here we have a sort of independent chemical evidence that supports also that this framework is at play. I also want to note that in this scenario, we do have a real connection between the organics that are formed in the interstellar medium and that are incorporated into icy bodies. So if you're only losing 10 or 20% of your interstellar material in forming these pebbles, then you have a kind of plausible way of delivering these molecules that are synthesized in the interstellar medium to terrestrial surfaces via impact. So I think that's also a nice connection that we can make. All right, so we've seen how we can build up chemical complexity in the early stages of star formation, and that some of this complexity can indeed survive the stages of disk formation and evolution. So I now want to talk about the role that reprocessing within the disk is playing in shaping the end kind of compositions of planet forming material. So we've only actually been able to study complex chemistry in disks in the past few years, thanks to the advent of ALMA. So the first detection of a complex molecule was made in 2015, this molecule methyl cyanide, followed by methanol in 2016. And so this is really very recent, and we're only just beginning to understand complex chemistry in disks. Questions like, are these complex organics common or rare in disks? Are they inherited from earlier stages or formed through disk processing? And are they important or minor species as far as the total volatile budget goes? So we set out to answer some of these questions by surveying methyl cyanide and cyanoacetylene in protoplanetary disks. So jumping straight into it, we detected methyl cyanide firmly in 5 of the 6 disks in our sample. And additionally, we had 2 more tentative detections here and here. We detected cyanoacetylene firmly in 5 of the 6 disks in our sample. And so this is showing us that now that we actually have the sensitivity to go looking for these complex molecules in disks, we're finding that they're fairly common. So we want to understand how important these complex nitriles are as carriers of the nitrile bond. And to do this, we can construct a physical model coupled with an abundance profile to basically do an abundance retrieval. So here I'm showing the outcomes of this type of model, where we have the observations on the top and the model in the middle. And you can see that our models does a very nice job of reproducing the observations. And so we can pull out these abundance profiles that look like this. So this is showing the ratio of the complex nitriles relative to a simpler nitrile HCN as a function of radius in the disk. And what we see is that in the inner 100 AU of the disk, methyl cyanide is between about 1 and 10% with respect to HCN, and cyanoacetylene is as abundant as HCN in some parts of the disk. So we find that these complex nitriles do seem to be important carriers of the CN bond at the radii in the disk where comets are forming. So if we're interested in considering sort of the total volatile reservoir in disks, this is also telling us that we need to consider the contribution of these larger molecules as well. All right, so how does this complex nitrile chemistry in disks compare to the earlier stages? Here I'm showing the methyl cyanide to methanol ratio, methanol just being the sort of oxygen-bearing analog of methyl cyanide. And this measurement has only been made for one disk, the TW hydro disk, where the ratio between these molecules is about unity. And we have 2 other upper limit or lower limits that are also consistent with a ratio of about unity. So when we compare this to the methyl cyanide to methanol ratio that's been measured in earlier stages of star formation, we see that we are now about 2 orders of magnitude higher in methyl cyanide to methanol in the disk stage compared to these earlier stages. So we see this strong enhancement in nitrogen compared to oxygen-bearing organics in disks relative to earlier stages of star formation, which is a pretty dramatic effect. So how do we explain this? There's actually a pretty compelling kind of framework that can explain why nitrogen is so enhanced relative to oxygen in disks. And it has to do with how the physical and the chemical evolution of the disk are coupled. So the idea is that you start with a disk where you have small particles sort of distributed throughout the vertical extent of the disk. And then as you have dust growth and settling to the midplane, these small particles kind of carry their icy mantles with them, locking them in the midplane and leading you to have an atmosphere that's very depleted in gas phase oxygen, but a midplane that's very rich in water ice. So the sort of takeaway here is that as a result of grain evolution, oxygen is sequestered in the midplane. So predictions are that in an oxygen-poor gas, you'll actually promote a very reducing chemistry, meaning the production of molecules like nitriles and hydrocarbons should be very efficient. So this can sort of qualitatively explain why we see this really kind of exceptionally bright emission of the complex nitriles like methyl cyanide. But it hasn't actually really been explored whether this oxygen depleted gas framework can systematically explain the emission patterns that we see in disks. So we set out to test this using a survey of 14 protoplanetary disks looking at the hydrocarbon, nitrile, and oxygen chemistry. For disk science, 14 is actually a pretty large sample. So trying to really sort of test the underlying chemical frameworks with this. So here you can see the C2H, HCN, and CO emission for a subset of our disk sample. And you can see that, first of all, they're just really beautiful images, but we also have a great diversity in the emission patterns that we see, both sort of for a given molecule from disk to disk, and also for the same disk seen in different molecules. So this diversity in emission is really speaking to the fact that we have a chemistry that is sensitive to the different physical environments, and that is kind of leading to these very different outcomes in the emission patterns. So we derived the C2H and HCN abundances for these molecules in our disk sample. And we found that the C2H and HCN abundances are actually correlated in the disks. So this, again, supports our notion that the hydrocarbon and nitrile chemistry is related through perhaps this oxygen-poor disk gas, where in sources where you have very kind of abundant hydrocarbons, you also have abundant nitriles, consistent with this reducing chemistry driven by oxygen-poor gas. So all this is sort of to say that with these more statistical samples, we can actually start to test the underlying mechanisms that are leading to the production of different molecules in disks. Now, I want to step back and think about the implications of this for origins of life chemistry. So this is a prebiotic chemical scheme coming out of the Sutherland group. And you can see that sitting at the center of this synthetic scheme is the molecule hydrogen cyanide. So it turns out that nitriles are actually kind of cornerstone molecules in the prebiotic production of molecule groups like RNA, protein, and lipid precursors. And it's actually really been quite interesting that the oxygen-poor environment in disks seems to be uniquely efficient at producing both simple and complex nitriles relative to earlier stages of star formation, and that this may actually be sort of an important stage for generating this class of molecules prior to planet formation. All right, so this then sort of leads to the question of when does the disk gas actually become oxygen poor? When does this sort of distinctive reducing chemistry emerge? So this is especially important to address in light of growing evidence that planet formation seems to be already underway in the early kind of disk stage. So this is perhaps some of the more beautiful representations of the early planet formation, where you can see that these very dramatic rings and gaps in the millimeter dust are already present in disks that are embedded in their parent envelope. So like I said before, we sort of historically thought that planet formation was taking place in these mature protoplanetary disks, but we're now really learning that the early stages of green growth are already underway in this embedded stage. And so we naturally want to understand then, what is the composition of the planet forming material in these early stages, the embedded stages, and does this very distinctive kind of reducing chemistry also play out in these younger objects? So we set out to address this by surveying chemistry in 5 protostellar disk candidates. So these are all embedded objects less than 1 million years old. And here's just the gallery of a few of the lines that we observed for 3 of the sources. And you can see that we have in some of them tracers like C18O and H13CN, this very kind of compact rotating emission on small scales in the protostellar core that's perpendicular to the outflow structure. So this is kind of exactly what we would be looking for when looking for emission from an embedded disk. And so with these high resolution observations coming from ALMA, we can now really start to distinguish the chemistry in the protostellar disk from other structural elements in the protostar and really say something about the composition of these young disks. So coming back to this question, we're going to use C18O as a proxy for the oxygen content of the gas. And so here I'm showing the C18O abundance for the embedded disks in our sample, shown in yellow and orange, and then compared to the more mature disks shown in pink and purple. And we then want to understand sort of when does the CO become underabundant relative to the interstellar values. This is a bit of a difficult comparison to make because even CHNO can be optically thick in some disks, but we can use some more conservative benchmarks accounting for this optical depth effect. And with this conservative estimate, we see that the youngest embedded sources are still sort of consistent with an interstellar CHNO abundance. But by the class 1 stage, or sort of 500,000 years, it's very difficult to reconcile our observations with an interstellar abundance. So we think that the depletion now seems to be happening by the end of the embedded stage between maybe 500,000 and 1 million years. And this means that this oxygen-poor gas, or this reducing chemistry, is established fairly early in the disk lifetime and then perpetuated throughout the rest of the disk lifetime. All right, so I want to take a minute to just talk about sort of what the next step in this type of disk observations is. So this is a sort of gratuitous image showing the comparison of the same disk observed in the same line with the SMA, with moderate resolution by ALMA, and with high resolution by ALMA. And you can see that we now just have this exquisite detail that we can see in the patterns of emission within the disk. So this far right image is taken as part of the ALMA large program maps, which surveyed 5 disks at very high spatial resolution. And this, I think, is really kind of a great development in our ability to characterize the chemistry of planet formation, because we can now actually zoom in on spatial scales that are relevant to planet formation. So a lot of our previous inferences of disk chemistry and how different molecules are related is based on bulk disk properties, but we can now really kind of resolve patterns within the disk emission and say something about what's happening much closer to the star. So I'm just going to briefly highlight work looking at the chemistry of simple nitriles in the disks as part of the MAPS large program. So this is a gallery of the CN emission observed towards the 5 MAPS disks. And we can now, like I said, start to really discern how the nitrile chemistry is varying across the disk. So this is, you're looking at the CN to HCN ratio as a function of radius in the disk for the 5 MAPS disks. And we see these huge variations in the relative nitrile chemistry, sort of 2 orders of magnitude variation in the CN to HCN ratio. So it's really exciting that we're now able to sort of make these very detailed measurements. And this actually tells us really useful information about the physical conditions in the disk that are driving the production of these different nitriles. So I won't say too much more, but the MAPS papers recently came out on the archive, so please have a look if you're interested. Okay, so a lot of what I've talked about up until now has focused on carbon, nitrogen, and oxygen. And that's for the very practical reason that we can really easily detect carriers of these elements at all stages from diffuse clouds through protoplanetary disks. Now, there's sort of an outlier. Phosphorus has actually been very challenging to detect in astrophysical settings. So I now want to say sort of a word about where we're at in understanding the phosphorus astrochemistry. So to do this, we actually have to step back to the protostellar stage. Phosphorus has never been detected in a disk. We were very excited a few years ago to detect phosphorus molecules PO and PN towards the protostar B1A. So this was just the second time that any phosphorus molecules had been detected towards a sun-like star-forming region, or a low-mass star-forming region. And you can see these nice detections made with the IRM 30-meter telescope that allowed us to make some sort of preliminary constraints on the phosphorus chemistry in this source. But what's really exciting is that we recently got follow-up observations with ALMA. And so we now have both spectral and spatial constraints on the phosphorus molecule emission for the first time in a low-mass protostar. So you can see here the white contours are the continuum, and then the colors are showing the PO and PN emission. We have some really interesting kind of differentiation between the PO and PN emission, but they're both sort of localized to these 2 clumps that are offset from the continuum. So we can use these observations to now sort of answer some questions about how phosphorus is stored in the interstellar medium. And the first thing that we wanted to do is to compare this clumpy emission of phosphorus to other line tracers. So here, the white contours are showing the emission of SIO. SIO is a high velocity shock tracer. And so we're seeing actually sort of a monopolar outflow coming out of the protostar here. But what was surprising is that the phosphorus molecules seem to be emitting sort of adjacent to the outflow, but not actually within the outflow, which is what we expected. So we looked around in our data for other molecule tracers, and we found that CCS is a dense gas tracer, and it traces this very kind of clumpy filamentary structure in the protostar. And what's really interesting is that the two spots where we detect phosphorus molecule emission are actually the regions where the protostellar outflow seems to be interacting with this filamentary structure. So this is sort of telling us for the first time that phosphorus is being released into the gas in regions where an outflow is actually encountering a kind of clumpy filament of interstellar gas. So we can also look then at how the phosphorus molecule emission compares to low velocity shock tracers. So here you're looking at the comparison with SO2 and methanol, and we see that the phosphorus molecules are co-spatial with these low velocity shock tracers. So we can put these pieces together to, again, say something about what is the storing phosphorus in the solid phase in these regions. So we know that the parent phosphorus carrier is more volatile than silicates because it's showing up with these low velocity shock tracers. But we also know that it's less volatile than simple ices because we don't detect phosphorus molecules towards regions like hot cores or hot carinos. So we can look at the volatility of different candidate phosphorus carriers, and we see that the metal phase phosphorus, things like schreibersite, are actually close in volatility to silicates, and so this is not a good candidate carrier for the phosphorus molecules in this source. Instead, we think that something like phosphorus oxides or mineral phosphates have a better volatility match to the emission patterns that we're seeing. So I think it's really exciting that we can actually say something about the refractory or semi-refractory material in these regions based on these phosphorus molecule observations. All right, but nobody likes n=2 science. So we're also working to expand the number of solar type star forming regions where phosphorus is detected. So we led a 30-meter fishing expedition for PO and PN towards 7 sources where we have very well characterized outflows. And we've actually found phosphorus molecule emission now towards 3 new sources. So this is great. We've more than doubled the number of protostars where these phosphorus molecules have been detected. And this is work that's being led by Serena Wormser, who's an undergrad at Harvard. So with this increased sample size, we can actually start to constrain how and when phosphorus is released into the gas. So, so far we found no correlation with any source physical property. We've looked at things like the age and luminosity, and you can see here, for example, that phosphorus is detected towards very young and very old sources. So there's no real trend here. The only trend that we've been able to identify so far is that we seem to detect phosphorus preferentially towards sources that have high water fluxes, which is a proxy for outflow shocking. So again, this is sort of matching our expectations that something about the outflow shock is really driving the release of phosphorus into the gas so that we may observe it. All right, so I think I'll just summarize now. We started this talk thinking about how chemical complexity can be built up in the early stages of star formation. And we saw how we can use tools like lab astrophysics to really constrain in detail the mechanisms that are leading to the production of organic molecules within ices. We then saw that there's plenty of evidence within our own solar system that some of this material that formed very early in the star formation sequence seems to have been preserved through the formation of icy bodies, and that there is indeed sort of a plausible way to explain this inheritance of organic material from the early stages. And lastly, we saw that disks have a really distinctive chemistry compared to earlier stages as a result of this coupled physical and chemical processing, and that it leads to the production of both simple and complex nitriles very efficiently, which are molecules that we're quite interested in from an origins of life perspective, and sort of suggests that the disk may be playing a very special role in producing these molecules. All right, so by synthesizing all of these different observational lab and modeling constraints, we actually can start to assemble a more complete picture of the chemical environment that planets are forming in. So with that, I'm happy to take any questions.
Thanks, Jenny, for this amazing talk. The floor is open to questions. If you have questions, you can either raise your hand or type them in the question and answers. Yeah, Andre, you have a question. You can unmute yourself and ask it.
Yes, hi. Thank you very much for the great talk. I have a question about the inheritance of, complex organic molecules and simple organic molecules. And you have discussed the inheritance from the star formation phase to the disk phase. Clearly, if you think about life, it would be very interesting to know what you think about the inheritance from the disk to planets. You mentioned HCN, right? But is that it? I mean, in terms of complex organic molecules, are they completely erased when you form planets, or do you think planet can inherit more complex molecules?
Yeah, I mean, I think that perhaps the material that's directly incorporated into planets as they're forming is not going to survive. We know that Earth basically melted at some point, and we don't really expect molecules to have survived that. But subsequent delivery by icy bodies like comets and asteroids could certainly have been sort of a later addition of organic material to the surface that could have jump-started some sort of origins of life process. So I think that that's the more like plausible route for how these inherited molecules would participate in origins of life chemistry. As for the role of the disk sort of beyond the nitriles, it sort of, I think, is not, it's not really clear yet, because for similar reasons, like I was talking about earlier, we expect a lot of the icy material to be present in the midplane of the disk, but we also know that it's cycled up to the more UV exposed layers. And so I think in order to produce more chemical complexity, you do need some energy source like UV. And so I think it's partially dependent on how efficiently that icy material is migrating to the sort of processing layers of the disk, where you could have more complex chemistry happening.
Itao, you can go ahead and ask the question.
Tao is muted. Can he unmute himself?
Hello?
Awesome.
Okay.
Yeah, okay. Sorry. Again, great talk, thank you. And I have a question regarding the first part of the talk. And when you talk about the like mesonational formation by the excited oxygen, atom formation by photo dissociation of those oxygen-bearing gas molecules. And I wonder if there's a way that you can analyze the isotope composition of your produced organic molecules in comparison with the carbonaceous chondrite organic molecule isotope signatures. Because as far as I know, if you have different light source or you have different starting oxygen-bearing molecules, you may have drastically different isotope compositions. So I just wonder if there's a mean that you can tell whether the way you're proposing that to form those mesonational molecules may be happening in certain region of the solar system, or and or whether it's a predominant process.
Yeah, that's a great question. It's not something that I've done, but in principle, you definitely could sort of explore multiple different ways of forming methanol through various sort of proposed channels, and try to understand sort of how the fractionation would play out in different through different mechanisms. So yeah, not something that I've done, but definitely possible, and a really interesting way to sort of connect back to what's seen in the pristine material in our solar system.
Great, thank you.
Okay, I think there is this question, the Q&A. I think you have answered some part of this question, but I'll just read it out. And if you have something more to add. Thank you for the brilliant presentation. I think we can assume that the potential building blocks of life accumulate or settle on the planets and the moons from the very beginning of planet formation. However, the temperature of the protoplanets are quite high, that chemicals can evaporate quite early from the surfaces. Do we have any data on what are the chances of these planetary bodies to preserve the organics until they cool enough to start the process of the origin of life? Or these processes are more likely to trigger after the secondary return of the organics on these planets as the temperatures decreases via volcanoes, meteorites, etc.
Yeah, so I think it's the latter, that it would be a sort of secondary delivery of volatiles that would have to participate.
Okay. Are there other questions that? I have a few questions that I would like to ask. So you kind of like, I think you talk about thermal processing in the disk itself, about organics like at a different temperatures of thermal stability. Like basically, but when we look at organics in meteorites, for example, they're super complex and they contain many different phases that have thermal stabilities that lie over many different temperature ranges. So when you define thermal stability, like, do you define it by a particular phase at a particular temperatures? Because like, I think what we understand from our solar system is could be very complex.
So do you mean like the thermal desorption of different molecules?
No, I think like you have in the section, right? Like you have like the stability of these phases, like in the mid plane, the stability, I think you had a region. Yeah, in that region, you kind of talk about the thermal stabilities and like at different, the 20 AU or 50 AU, like, so basically, like that's what I was trying to refer to. Like when you talk about thermal stability, do you talk about like a single phase or like a very simple molecule? Because like inherently the thermal stability should be a very complex feature as far as we know from organics in meteorites.
Yeah, so in our model, we're just considering simple ice molecules that, again, we're kind of testing whether the ices that we know are present in the protostellar stage could survive their journey. And so it's things like water, CO2, methane. And so in that case, there's a pretty straightforward way to characterize their thermal stability on the ice, just in terms of whether they will desorb above a given temperature. We're not including more complex like refractory organic material, but at least in the regions of the disk that we were looking at, I don't think the temperatures would get high enough to really affect that. It's possible that you could have some further UV processing in the upper layers of the disk, but yeah, it's hard because we don't know sort of the initial conditions starting in the ISM for what material to start our model with. So it's hard to say then what happens to it in the disk stage.
And I think another question that I had was, you kind of talked about organics formation in the ISM or in the molecular clouds themselves. But like, I think for our solar system, it has been postulated that you could kind of form organics in the colder and outer regions of the protoplanetary disk. Do you consider, do you take those things into your account for those things into your models as well?
So the model that I showed here is a very simple model, just looking at destruction, because again, it was a very particular question that we wanted to ask of whether this material could survive. We weren't looking at molecule formation, but that being said, I think definitely there are processes that can happen in the colder disk region. So the oxygen atom chemistry that I talked about in the beginning of the talk, that was sort of in the context of cloud or envelope chemistry, but the conditions are similar. You would have low temperatures and some moderate UV field. So there's certainly types of chemistry that could be happening in colder environments that could still be producing organic complexity in the outer disk.
And one last question about your experiments, like it's kind of related to Tao's question as well. So basically, when you talk about these experiments and you talked about like formation of these basic organic molecules in your experiments, like what would we understand is like when you kind of form some organics from some gaseous phase, you see a huge isotopic composition difference? Like, do you plan to think about those kind of things? I think people have done experiments where they have actually kind of looked at, like, when you go from a gaseous phase and then you form organics, you kind of see a huge isotope fractionation. But like, I think in your, can you incorporate those kind of things in your experimental systems, or is it not possible?
Yeah, I mean, you can definitely look at how different isotopes would behave. It's, again, not something that we've done yet. I don't think that the effect would be as strong as what you see in the gas phase necessarily, because again, when things are in the solid state, the energetics are just a bit different. So yeah, I'm not sure that we would expect to see as strong of a fractionation signal, but you could definitely test it, and it would be really interesting to do.
All right. Are there any more questions from the audience or the panelists? All right. Okay, I don't think we have any more questions as of now. So again, thank you, Jennifer, for this amazing talk.